Okay, so the first thing I'll mention, and I believe I posted this in the announcements, but I'll add it here, is that don't forget that I posted the assignment for the research critique. It is posted on Blackboard on the main assignments page. Let's see here, I can share that. Not here. Let me put it up. That'll ask me to put it up. So I log into Blackboard. And go into the assignments. It's right there, right at the top. So make sure to go in there, read the guidelines, so you can get started on your new story and study submission. That's important. All right, now let me talk a little bit about probability in general. We're not going to go too deep into probability in this course. And then also talk about there it is. And then also talk about, more importantly, probably about the second half of the module, 6.2 with the normal distribution. And as always, jump in, use your chat box if you have any questions. Let's see here. Bring this up. Back in Module 2. Alright, Module 6. Alright, so we're going to talk about probability in Module 6. Alright, so as it says, we talk about probability as the likelihood or chance. Basically, the way I tell students to look at probability, but not the way that a lot of people do intuitively, is that probability is what happens over the long term. So if we say, for example, that the probability of getting heads when you flip a coin is 1/2 or 50%, that means as you flip a coin a large number of times, we expect to see about half come up heads. That's really what probability means. Probability allows you to predict long-run results. Now, if I flip a coin 10 times, I could end up with quite a few heads, or not very many. But if I flip it a lot of times, it should be pretty close to 50% heads. And that's what this first part of this tells you. And then these are things that this sort of, did I get this? I know it's hard to see. There's no easy way for me to make this larger, sadly. But an event that's impossible has a probability of 0. So events that are unlikely are closer to 0. Events that are very likely are close to 1. And then events that are a little more likely than not are a little more than 1/2, or vice versa. Events maybe a little less than 1/2. Alright, so the probability that an event will occur is a number between 0 and 1, as this says. And then in terms of probability notation, we type P of A for the probability that some event A will occur. So right here, we have P parentheses heads equals 1/2. That little greater than symbol isn't supposed to be there. And that's the, as it says, the theoretical probability of getting ahead. But what it really means is that over the long term, if you do lots and lots of coin flips, you'll get heads on approximately half of them. In other situations, though, it's a little trickier to calculate probability. So that's what this talks about here, is based on enrollment data. you have to use actual numbers and to do the calculations instead of theoretical. We haven't flipped a coin all the times that it can occur, all the times that it can be flipped, because that's impossible. But we can look at all the people who attend the college and figure out what percentage of them are female or male. Okay. So we have probabilities that we sort of base on the theory, like the probability of getting heads on a coin, and probabilities that we base on data that we've gathered. That's what this has said. What does it mean when we say that the probability of heads is 1/2? And then we use an applet to simulate flipping a coin. You should go and take a look at that. But basically, the idea is that the more times you flip the coin, the closer it'll get to 50-50, the overall results. Let's see here. That's the big idea to take from the first part of this, the very first part of this. Let's see here. All right, well, what about calculating probability? That's really kind of one of the things we have here. Here's the different types of bloods, ignoring positives or negatives. Yeah. Can you get all the way over there? Yes. So when you see P with a parentheses around something, that means you're calculating the probability of that thing. So let's see. So here we've got just the word probability, but if you said, you might see something written like P parentheses A, and that would mean the probability of blood type A, which is 0.41. So, and this table here represents a probability distribution where all of the numbers represent probabilities. There are all the possibilities that if you added up all those probabilities, they would add to 1. Because those are all the things that can happen. Someone can only have one of those 4 blood types. So if we randomly select someone, then this question basically is asking what's the probability that they have blood type O, and that's what that P means. And it's 0.45. So, and that's just the number under the O there, right here. And another way to think of that is that 45% of people have blood type O. So you can always think of probability as in 2 ways. The probability for a single outcome, so the probability that if you pick one person that they're blood type O, or you can think of it as the percentage of the whole population. Excuse me. The probability that everybody, that 45% of everybody is a type O. That's the same way with coin flips, that the probability for one coin flip that it'll come up heads is 1/2. And what that means is 50% of all coin flips are heads. All right. So this is just an example where the number of eggs in a randomly selected nest follows this probability distribution. Looks like 3 or 4 are most common. Let's see here. So these are some things about probabilities. The biggest things are the last 2, that the probabilities all have to be between 0 and 1 because that's what probabilities are, and that they have to add up to 1. And of course the fact that they have to add up to 1 is important in the first of the 2 quizzes in this module. All right. Let's see here. I'm trying to get it to go to the next page. Good. All right, so some probability rules. Basically, the key with the first of the probability rules is that if you see the word "or" in your probability statement, that means to add the probabilities. Mostly. You actually, in the last module we saw that OR didn't always mean to add straight up. So here we're able to add, but that's because there's no overlap in blood type A or blood type O. If there is some overlap, you just add, you've added them twice, so you would need to subtract off the overlap, which was the case on the quiz from Module 5, which I'll have graded later this week. So we call this the addition rule, but basically, as this says, probability of A, here's our addition rule right here, probability of A or B equals the probability of A plus probability of B. But the key header for that is the two events have to be what we call disjoint. That is, they can't both happen. There's no overlap between the two events. That's what disjoint means, is they can't both happen. In this case, a person can't have both A and O blood types. They're one or the other. And also the nest can't have, for this question too, the nest can't have 0 eggs and 1 egg. It can only have one or the other, so those two are disjoint. So when can we not add probabilities directly? Well, here's the question right here. It says, what's the probability that a randomly selected student from this table, which I think might have also been in Module 5, is either a health science major, or a female? Well, with the reason why we can't just direct add them is because here's the health science majors, there's 644 of them. Here's the females, 6,198. But if we just add those, then we've counted 421 people twice. The people who are both health science majors and females. So the sort of what we need to add to the addition rule, so to speak, is that if they overlap at all, you have to subtract off that overlap. So we could add the 644 and the 6198, but then we'd have to subtract off the 421. So that's what they do down here. They add the 644, 6198, and subtract off the 421. And then they end up with that probability. All right, so says, do we ever subtract probabilities? Well, sometimes we do, and that's if we are finding the probability that something doesn't happen. Sometimes we subtract the probability from 1. So this is sometimes called the complement rule. But the probability that something doesn't happen, i.e. that someone's not a universal blood donor, that is, their blood type is not type O, is always 1 minus the probability that it is, because those two events make up everything that can happen, and they don't overlap. So we call those events, sometimes we call them complements. All right. And sometimes the complement is easier to calculate. So in this case, it says, what's the probability that a nest is not empty? Well, not empty means it has more. It has 1 or more eggs. Well, I'd have to add up 6 numbers, but based on the way the table works, I could just take the 0.2. That's the probability that it is empty, and subtract from 1, and then that would be my 0.8. So that's this calculation right there, as opposed to adding up all the rest of the probabilities, which gives me the same answer but was more work. So anytime you see, and this is the most common place where we see the complement rule, is the probability of at least one of something is always 1 minus the probability of none. So here we have the probability of at least 1 egg. That's equal to 1 minus the probability of no eggs, or 0 eggs. All right, so it's called the complement rule. And there it is right there again. Probability that A does not occur is 1 minus the probability that it does. All right. All right, so a few more rules. Independence and conditional probability. We talked about conditional probability in Module 5. Um, but usually we do it with tables, and tables are easier to do it with than using formulas. So here we're looking at probability that someone is a health sciences major versus the probability that someone is a health sciences major given that they are female. So the probability that someone is a health sciences major in general is the number of health science majors, 644, out of the total population of 12,000. The probability that they're a health sciences major given that they are female, so the key here is given that they are female. That means we're only looking at the females. We're only looking at that row right there. So for the females, 421 out of 6,198 of them are health sciences major. So that's what goes on down here. There's the 644 out of 12,000, which is 0.54. That should be 0.054. That's a typo there. Versus the 421 out of 6,198, which is 0.068. So someone is more likely to be a health science major if they're female. So one thing they say is we say that gender and whether or not someone is a health science major is not independent. That is, whether or not they are a health science major depends on whether or not how likely it is that they're a health science major depends on how likely it is that they are female. Let's see here. And there's not much about that in the quiz on this section, so I'm going to kind of go beyond that. We're really more interested actually in the next section. Let me go back up to the top, make sure I got the right page. Yeah, random variables. So basically, what a random variable is, let's start here, is it's just a variable. We use a letter usually, most commonly X, where it's quantitative and it's the result of some sort of random situation. So here's some different number of boreal owl eggs in a nest, number of times a college student changes majors, shoe size, weight of a student, foot lengths for adults. So they're random variables if they're the result of something random. So it might be, in the case of the owl eggs, maybe we choose a nest at random. For the college student changing majors, we choose a college student at random and find out how many times they've changed majors. And then we would call X, we would say the answer for that is X. Now there's two types, and we're first going to deal with the discrete type. The discrete random variables means it can only take on a whole number. So usually that's a count, like the number of eggs, the number of times someone changes major, or it could be something that's divided into whole numbers or some regular interval of numbers, like shoe sizes. So shoe sizes, can be like 5, 5.5, 6, 6.5, 7, 7.5. Because they come at regular intervals like that, we call them discrete. But things that are usually the result of measuring, like weight and foot lengths, those would be continuous. But we don't use random variables for categorical things like blood type. It has to be something numerical. All right. Let's see here. So now we're going to look at probability distributions, as it says. All right. So now basically it's very similar to what we were doing, but now we're going to use a variable X for whatever it is we're measuring. So here we're going to say X is the changes in major. And then underneath each of those values of X, 0 up to 8, there aren't very many people who change majors 8 times, but they are there, is its probability. So those are all the possibilities and the probabilities of each one. And then they give what they call a probability histogram, where each bar has width 1, and then the height of the bar is the probability for that number of major changes. So the higher the bar, the higher the probability. So now, here's some features again, and these are very similar to what it was before. The outcomes are random. We have a way to assign probabilities, and the probability is the relative frequency of the outcome, and the sum of all probabilities has to be 1. And again, they can either be theoretical or they can be empirical, based on data. So this one is based on data. All right, so one thing I'm going to do, I'm going to add this to it, and this is because it's in the notes, but I also want to do it here. So it says, what is the probability that a college student will change majors at most once? And it says that means that either x equals 0 or x equals 1. So I can add because it's an or. But I can also write this with an inequality. And that's something I like to do. They don't do this on OLI. And I'm going to say, I'm going to bring up my little writing pad here. Well, I guess I could have done it in another program, but that's okay. All right. So if I'm talking about the probability they change majors at most once, that means 0 or 1 times. So that's the probability that x equals 0 or x equals 1. But we could write that more simply by saying the probability that x is less than or equal to 1. Or we could say, if we prefer, probably that x is less than 2. But based on the way the statement is written, at most once we would probably use this one where it says less than or equal to. And we would go to our table and look at the values of x that are less than or equal to 1, which are the ones that are in yellow, and then we would just add those probabilities. We would add all the probabilities for all of the x values that we had. And so we didn't do just what they did there. So when it says to write an event, like on the quiz, as an inequality involving x, that's exactly what you're seeing here. But if it's just the event, that's that they change majors at most once, then we wouldn't actually write the p. So x is less than or equal to 1 means the randomly chosen student changed majors at most 1 time. If I want to find the probability of that, that's when I put the p. So without the p, it's just talking about the event. When you add the p, that's talking about finding the probability of that event. All right. John's parents are concerned that he's decided to change his major for the 2nd time. John thinks he's not that unusual. What is the probability that a randomly selected student will change his major 2 or more times? So see, they have to write all of this here, when it would be easiest, 2 or more times would be, then I would write, if we want to find that probability, the probability that x is greater than or equal to 2. So in the parentheses, that's the event. Someone changes majors 2 or more times, and then stick a p in front of it to talk about the probability. All right, so they show you a couple different ways to calculate that. So as they say, changing the majors happens about 2 or more times, not that unusual. It happens more than half of the time. So they say, how often would he have to change his major to be considered unusual? And then they just started adding the probabilities from the top, from the least common, starting down. And then when they got to 5, when it got to 0.053 or 5% of the time. So it says that's pretty unusual. So someone changing their majors 5 or more times is pretty darn unusual. But it does happen, about 5% of the time. All right. So, and then they talk a little bit more. All right. Now, mean and standard deviation. The mean is the same thing, by the way, as the excuse me. The mean is the same thing as the expected value. So when you see E of x on the quiz, that's the expected value. You can see that also in the on-site notes. So they show you how to calculate it here, but I'm not going to bother with that. In fact, I'm going to go back to the previous example. I'm going to calculate the mean and the standard deviation of this distribution of major changes right there. Okay, so I'm going to bring up the calculator. I'm going to do this using the calculator. I can probably move my calculator a little bit to see the table. Oh no, I can see the table there. So stat, and it's stat and edit to do this. I'm going to clear out my list. I'm going to go up to the top of the list, press clear, and enter. Go over to do that for both list 1 and list 2. Okay, and then I'm just going to put in list 1, I'm going to put all the values of x, so 0, 1, 2, all the way up to 8. Okay, I'll use the keyboard on my computer there. And then I'm going to put in each probability. I don't really need the leading 0. So that's what I do here. Bear with me for just a moment while I do this. And I'm going to ignore the 9 because it says 0.000. I think in the first table they didn't even include that, so I don't need it. But the probability of 0, I don't have to include it. Now, the way to find the mean here is the same way we did it, or the expected value is the same way we did it in when we were in Module 2, when we were taking data from the test. We would go stat and calc, and we're going to do the 1-var stats, number 1. And then I would do L1 and L2, because normally if you just do 1-var stats and hit enter, it's do 1-var stats and hit enter, then it's going to be it's going to just look in one list. But I need to tell it that I have frequencies in another list, or in this case, relative frequencies. So I hit enter, and you see the mean there up at the top, 2.002, pretty much 2. Even if I round to 2 decimal places, it'll be 2.00. And then normally where we look for the mean is S, but it's blank. And so actually we're going to use that little O with the tail thing as our standard deviation here. And so that's about 1.42. So if we talk about the mean, in this case, so the mean, we can write it one of 2 ways. Either we can use, not the X bar symbol, but we use a little, this is a Greek letter, it's a lowercase mu. You can sort of see that it's M-like. It looks almost like a cursive U. But it's the same thing as that E of X that you see on the quiz. That's the expected value of your random variable. And that's about 2. And then the standard deviation, which is that little O with the tail, was about 1.42. So what this tells me is that on average, students change their majors about 2 times. Standard deviation, so the variation from that is about 1.42 changes a major in either direction. So that's all you have to do to find that value in the last one. And all it tells you is the long term. So in this case, you could look at it as, on average, people change majors 2 times. If we want to think of it more sort of quote-unquote correctly, but I'm not picky about it, in terms of the random variable, it means if we ask lots and lots and lots of people how many times they changed majors in college, on average, people would say twice. So that's actually all you really need for a quiz, whichever, I can't remember the quiz number now, but the first quiz in Module 6. Let's see where we are. So we still have some time. I'm trying to remember if there's something else important that I need to do in this topic, because we're only on the first page of it. So let's see, this part of it. Hey, we picked someone up here. All right. Standard deviation, don't worry about the, again, for both the mean and the standard deviation, don't worry about the calculations of it. Just learn how to do it on your calculator. Which, in addition to what I just showed you, is there's also a video linked from Blackboard. If you click the videos button on the resources pages in Blackboard, there's a video for how to do it there for the example in the notes. Right. So I'm not going to. Don't worry about the formula here. You do not have to use this formula at all. They show you how to use it. But what I would do if I were you is I would put the data into your calculator, the times here in minutes and the probabilities, the time in list 1 and the minutes in list 2, or probabilities, right, and the probabilities in list 2, and then do the 1 var stats of L1 comma L2 and make sure you get the right mean and standard deviation. All right. Let's see here. So let's just look and see if we have what key things we have here. Cover, because they're really actually module or 6.2 is probably going to also, so that's just more about the standard deviation. I don't think there's anything critical. And actually, the question on the quiz doesn't ask standard deviation, but I think there will be one on the next test for you for the standard deviation. All right, so there's the changing majors, and you'll see they got 1.4 for the standard deviation, which is what we got. They got 2 for the mean, which is what we got. So that would be fine. All right, let's see here. This is just an example. So that's good. This is kind of a nifty, you should definitely take a look at this. This would need kind of a neat example regarding how to find illegitimate tax fraud data. All right, so then let's go on to, well, first of all, pause for a moment, especially since we have someone who just joined us. So if there's any, I'll pause in a moment to take any questions you might have before I talk about 6.2 in the normal distribution. And I apologize for being, my allergies are bothering me tonight. Any questions before we move forward? Okay. All right. Then we'll talk about 6.2, the normal distribution, which applies to quiz 2. Well, the second quiz for this module, since like I said, it's not jumping to my mind. Okay, so quiz 2 you'll see is a lot. I'm not going to spend a lot of time on continuous probability distributions because those are basically just some examples. They're not anything you're going to deal with. But the basic idea with continuous probability distribution is instead of the values only being able to take on a whole number, they can take on any number within a range. So this is different. You can't just say the probability, you can't just start adding up numbers like we did here. You can't say, well, the probability that x is less than 2 is 0 and 1. Well, it could also be 1.5 and 1.58 and 1.32971. So those are all possible values. So that makes it a little bit more complicated. But the normal distribution is nice because what we can do is it's really, once you have this mean and the standard deviation, you have all you need in order to do all of your calculations. So the normal distribution is just our so-called bell-shaped distribution. We call it a normal curve or normal distribution. So that's basically the general picture of what it looks like there. And like it says, we call that the bell curve sometimes. Okay, they can be centered at different places. They can be wider or taller, wider and lower, or taller and skinnier. So that is with more of the distribution in the middle. Well, there's two things that control the normal distribution. One is the mean, and that's the location of the center. So here, the red curve and the black curve have the same mean of 10, whereas the green curve has a mean of 14. They are also controlled by their standard deviation, which is how spread out they are. The black curve and the green curve have roughly the same standard deviation since their spread is about equal. But the red curve has a higher standard deviation because its spread is wider. What I'll say here is that, and this is something that's in the first part because I sort of skipped by, but what the curve represents is that there's a certain area under the curve, and that area under the curve represents probability. So the total area under the whole curve, left to right, is 1, to represent a total probability of 1. Even though it doesn't look like it on this picture, the curve actually extends infinitely in both directions, but most of the area is concentrated within 3 or 4 standard deviations of the mean. All right, so we are still going to use, as we were before, as this says, the Greek letter mu for the mean, and the Greek letter sigma for the standard deviation. And you may say, well, why do we use these other letters instead of x bar and s like we were back in Module 2? It's basically the difference in Module 2, those were based on data, and they were just an estimate for the whole population. Well, these are, the mu and sigma are the mean and standard deviation of the whole population of everything. So we use a different symbol for those. All right, so this says basically what I was just saying about the same mean or same standard deviation. All right. So here's some interesting information about the normal curve. If you start at the mean, so here's a curve with a mean of 1 and a standard deviation of 2. If you go out 1 standard deviation in either direction from the mean, so you go from 10, you go down 2 and up 2, then that area is 0.68, or another way of saying it is 68% of the normal curve falls within that range. And then they give an example of that with some numbers. And it actually extends outward to 2 standard deviations and 3 standard deviations. So here they're just showing you that if you go further than 1 standard deviation to the right, if you take that right tail here, that's 0.16, and the left tail is 0.16. And those basically come from the fact that one important feature of the normal curve is that it is symmetric. That is, the area is the same on both sides. So if we take that 0.68 or 68% and we subtract it from 1, we get 32%, and divide it in half, and we get 16% on each tail. If you add up all 3 of those numbers there, 0.16, 68, and another 0.16, you'll see that they add up to 1, the total area of the curve. All right, so let's see here. Still doing the same thing. Oh, so if we go out instead of 1 standard deviation in each direction, if we go 2 standard deviations in each direction, the area is roughly 0.95 or 95%. And if we go out 3 standard deviations, it's roughly 0.997 or 99.7%. And so sometimes we call this rule the 68, 95, 99.7 rule because of how many standard deviations there are, how much area, there is within each number of standard deviations. So there it is in probability notation, that the probability that x is between mu minus sigma and mu plus sigma is 0.68, minus 2 sigma plus 2 sigma 0.95, minus 3 sigma plus 3 sigma is 0.997. So they call that, one name that sometimes is called the empirical rule, the other name it's called is just the 68, 95, 99.7 rule. Oh, we lost one of our people. All right. Here we lose. All right. So here's an example of using the empirical rule. Actually, you know what? You can go through the notes. Let me do it on my notes that I have here. Let me pull it up real quick. I've got some notes that I can show you on the. There we are. Let me pull this up and do it on here, because I'll just do a different example, and then you can look at the examples in the OLI as an additional. So these are the same notes that you would see on the class and the on-site notes in there, but they're not filled in here. All right, so let's see here. All right, here we go. This will work. Oh, did not mean to do that. I'm trying to get it to hide the left tab here. Let's see if we can get to it without it. There we go. All right. So it says if test was given and the scores followed a normal distribution with a mean of 75 and a standard deviation of 8, what percentage scored higher than 91? Well, anytime. So the keywords here are the normal distribution. Let me do this in blue. It's probably going to be in this. Right here, normal distribution. So what that tells me is it follows a nice bell curve. So any of these types of problems, I always tell students, draw that bell curve. I always draw it. I tell students they should always draw it. Not a very pretty bell curve, but it's not what's important. The mean always goes in the middle, so we got 75 here. All right. And then if I go one standard deviation out in each direction, 75 plus 8 would be 83. 75 minus 8 would be 67. So if I look in here, this would be 68%. Okay. Well, that doesn't have anything to do with my answers over there. But if I add 8 again, 83 plus 8 is 91. 67 minus 8 is 59. So if I do that, go out that far in each direction, now I'm at 95% by the rule. Okay, so the question is what percent scored higher than 91? So I'm looking for basically the area in this right tail right over here. Okay, well, so how can I figure that out? Well, if there's 95% in the middle, that equals 5% in the two in the left tail and right tail combined. So I got, if I call this area A and this area B, then area A plus area B equals 0.05 or 5%. Okay. Well, since the curve is symmetric, then the area on the right-hand side, the B area B equals half of that. So area B equals 0.05 divided by 2, which is 0.025. Or, since it says what percentage, I change that to 2.5%. Right? Or I could have just said, take that 5%, subtract it from, take that 5%, and divide it by 2.5%. If you choose one student at random, what's the probability that student scored higher than 91? Well, I just then give that as the decimal answer. So probabilities we usually give as decimals. And that would be the answer. I don't have to do any additional work there. And then there's a little symbolism here. I don't really do this too much, use this too much, but it's a nice, handy shorthand way of saying if we talk about a introduce a random variable x, the probability that a randomly selected, and say that's the score of a randomly selected student, then we say x, and that we say that little tilde there, we say it's distributed normally with a mean of 75 and a standard deviation of 8. Okay, I just put the little symbols there. Mean, the first one is the mean, and the second one is standard deviation. All right. So now we often talk about z-scores when we're dealing with the normal distribution. All right. So the way you find the z-score just tells you how many standard deviations a value is above or below the mean. So if you take if x equals a value from a normal distribution, right? Then its z-score, we just look at how far it is from the mean. We just subtract off the mean, and then how many standard deviations would be to divide it by sigma. Okay, so if we wanted to do that for the test score of 91, we take 91, we subtract off the mean of 75, and divide by the standard deviation of 8, which would be 16 over 8, or 2. And all that tells me is 91 is 2 standard deviations above the mean. If I had gotten a negative number, that would mean it was below the mean. So I guess that's actually the answer to the next question. So, okay. All right, and that 68, 95, 99.7 are empirical rule that we were talking about. That's for points with z's, as it says, that are integer values. What if our z's are not integer values? What if they're in between? So then those rules don't apply, but it's somewhere in between those values, the percentages. We're going to skip this example here. You can look at it in the notes if you want to. All right. Well, z-scores have a certain distribution. They are normal. Just changing the mean and standard deviation doesn't make it normal. If we subtract off the mean, then that moves the mean to 0. And then if we divide by the standard deviation, we're basically taking the standard deviation, dividing by itself, and you get 1. So normal. It's normal with mean of mu equals 0 and standard deviation of sigma, lowercase sigma equals 1. And we basically, oh, that's supposed to be a 1. All right, so as it says, since all z-scores have the same distribution, we can use z-scores to determine probabilities. Instead of the problem about test scores, let's determine the probability that a random student scored at least a B. So a B is 80, so that would be the same thing as, let me check this back here. So if X equals the test score of a randomly selected student, we want probability that X is greater than or equal to 80. That's at least a B. Okay, well, like I said, I'm always going to draw the normal distribution. So I'll have my 75 here, and my 80 is going to be here. So it's less than 1 standard deviation above the mean. I can calculate it. So at least means that much or higher. So I'm looking for this area over in the right tail. Okay, I don't have to be too harsh about it there. Okay, so how do I find that area? Well, one way is to find the z-score and to use the z-score with a z-table. And it shows how to do that online, and lots of students do that. But there's actually a function on your calculator that tells you exactly this thing, and it's called the normal CDF. And here's, you have to put in 4 entries, and it depends on what you're looking at on your calculator. All right, so if I bring my calculator up here, all right, if I do the normal CDF, here's where you find the normal CDF. You hit, and this is also on the course videos. If you hit second and the variables key, var is right under the arrow right there, you get this menu. If you see above vars, it says DISTR, so that's the distributions menu. I want the normal CDF right there, number 2. That's what I wrote. It stands for cumulative distribution function. And here are the entries it wants. It wants the lower bound of the area I'm looking for. Well, here's my area. That's my area. The lower bound of that area is 80. The left end point of the area is 80. So the first number I would put in is 80. Then I'd hit my color. Then it wants the upper end of the area. Well, there is remember I said the curve extends infinitely, even though you may think the highest test score could be 100. The curve extends infinitely in that direction. So I actually need to put in a really large number. Different teachers do different things. I usually just tell students to put in a good number of 9s. So I put in 5 9s. That's fine. And then the mean, which on the previous page we gave is 75, and then the standard deviation, which we gave is 8. Those are my parentheses, hit enter, and I get about 0.266. Okay, so I'll write that here, 80. I actually write infinity because that's really what it represents, but I just type in a large number, 75, comma 8, and the answer is about 0.266. And that's my answer, because that's that area that I just calculated right over there. Okay, so actually it says now let's determine the probability of the technology. That's what I did. So second, again, second, and the vars key is how I got to that. Okay, I'm not going to bother with the normal table. Okay, let's see what your question is. Yeah, what's your question? Sorry, there we go. Okay, so in the parentheses, let me go back to it. Okay, the first number is the left endpoint of the area. Sometimes I call that the lower endpoint, but we'll say, well, even if we just say left, that should tell you. Then right, and then the mean, and then the standard deviation. Those are the numbers there that those are. All right. Okay. So that's how you use that, and that's one of the questions on the quiz that you have to use. One you can do with the empirical rule, one you can do with that. Let's see, was there another question down here? Yeah. All right. Well, I'm going to add a question to this rather than go on to a different example because we're getting close to the end of time. Yeah. Okay. Yes, in the notes folder, yes, you'll find the same example. And it even shows what each thing is in there. And I think the video is based on the same example as well. But let's say here, let me change back to my pointer. All right. So let's suppose, instead of this question, let's just delete that question. What score puts a student in the top 20%? Okay. There's a little room here. All right, so let's see if we can figure this answer out. All right, well, like I said, I always start off with a bow curve. I draw the curve. Always, always, always. Oop. All right, well, the mean of 75 always splits the curve exactly in half, 50-50 on either side. So I'm going to go over here, and the top 20% would be over here somewhere. So this area would be 0.20. Okay, and it says what score puts a student there, so I'm looking for this x value, this value on the x-axis. Okay, so it's sort of, I'm working backwards from what I did before. Last time I had a test score, I wanted to find an area. This time I have an area, I want to find a test score. So if I go to my calculator, there's actually a function that does that in the same place. If I hit second and vars, and that's the inverse norm, number 3, that's sort of backwards. So I hit number 3, and this time it only wants 3 entries. But the first is the area. But it doesn't want the 0.20, it actually wants the area to the left of x, because you can't guess whether it's right or left, so it just always assumes you put in the area to the left. So I put in 0.8, and then I put a comma, and then I put the mean, and then a comma, and then the standard deviation of 8. And then close the parentheses, and the answer is about 80, roughly 82 if I round to the nearest point. And that makes sense, it's a little higher than 80 cut off 26.5% of the data roughly. So 81.7 cuts off the upper 20%. So if we write that down, so we did, to solve this, we did IMV norm, same place, second in the vars key. All right, and we did 0.8, 75, and 8. So that was about 81.7. But this area is equal to 1 minus, the area to the right is equal to 1 minus 0.20, which is 0.80. All right, and that first number is always the left area. And then, of course, the mean and the standard deviation. All right, so that's basically the idea. That's the key things you really need to get in order to solve the quizzes. There's some more stuff in OLI that's important and for understanding the concepts, but for as far as the sort of the basics for doing the quiz, those sorts of things. This is normal CDF and inverse normal will get you, and Z-scores will get you what you need for the quiz on 16. So with that said, go back to do you have any other questions for me, Danica, before we wrap up? Okay, well, what I'll say then is take a look over the quizzes, do as much as you can, look over the OLI, and then if you have any questions, of course, post to Piazza, and I will answer them as best as I can. I'll post the video up to Piazza in a little bit, in case there was anything that you wanted to go back and look at in the video. All right, have a nice night, and I will talk to you soon.